And the last speaker for this session is Professor Shiqing Wang. And yeah.
Yes. Relax, it's almost over. Coffee is on the way. Thank you for inviting me to come. I'm super excited. And I realized we can do two ways. If you remember everything of the previous two talks, I can cut my talk into 20 minutes. We have early coffee. Or if you want me to solve all the problem they presented, give me 35 minutes, just 5 more. Ron was very clever. He pointed out viscoelasticity is inadequate, but he didn't give us the answer. I hope I can give you an answer. I hope to convince you. So in any case, two community meet. There's just a few of us in polymers. Much of you many of you are doing mechanics. I'm going to try to learn both fields. How about that? And give you a report. Okay? So, needless to say, you are all my teachers, the speakers, because I started to look at fractal mechanics. I shied away. That's such a complex problem. I don't know. I'm a physicist. I don't know anything, unlike Michael. So, but my side is very clear. I want to really get your feedback about whether I have learned anything. Whether I have learned anything from fractal mechanics, and whether I have told myself a little more about polymer physics. I will raise more questions and answers, but the question that bothers me are these two. Are they really flaws that give me a low nominal strength, or there's something else going on? There's this energy dissipation? I should just turn off I was trying to make sure that the Zoom works. Okay, so here's the outline. Relax, I only have 18 slides. The rest of the slides are unimportant. Don't look at them even. So I was humbly reminded there are two approaches to mechanics. It's either energy or stress. Are they equivalent? Is there one over the other? Is there causality? I want to know that. I want to further shift all the blames to our pioneers, Griffiths. He has a 1924 paper, and as well as Reverend Thomas. Here are their quotes. They suspect this is all about stress reaching certain level at the crack tip. This is another. Reverend Thomas admit, oh, that tip is so small, I'm not going to resolve it. Let me be lazy and do the Griffiths approach. So here's my 3 students. They are the one who did all the work. So let me use a few slides, 4 slides, to just review what we have learned. And then I would talk about the previous 2 talks, the topic, the phenomenon of elastic fracture. There are several topics in that. I'm going to review what was the prevailing view and what is my view about it. I hope I will be convincing. So in any case, fracture is not a fracture mechanical problem if we don't blame flaws. In other words, fracture only is a problem if our nominal strength is much lower. I came from polymer physics, equipped with some understanding of our brittle glassy polymers, that I know these 2 stresses might be comparable. That was my starting point. If that's the case, in the uncut case, there's no business in fracture mechanics. But fracture mechanics does come back because when you have large crack, that's when things happen. So what I was hoping to do was, let's save all the time. What I was hoping to do is, can I validate? Can I really confirm that my nominal strength is my true strength, meaning strength in absence of flaw? So I'm going to try to peek into what Reverend Thomas didn't do, look at the peak and see what I can resolve, right? So here are the case of PMMA. We had a crack, and we do birefringes, and we see the butterfly. We try to analyze what the birefringing teaches about what's going on at the tip. And we find that barrier fringes levels off as you approach to the tip, which is to the right because I plotted as 1 over minus 1/2. And it has a comfortable zone. It levels off about 100 microns away from the tip. If that's the case, I can claim to know what is the stress at the tip and find that stress to be proportional linearly with the load, K. In particular, that linear extension goes all the way to the point of fracture. Therefore, I know what Kc is. It's determined by whatever the tip stress there, and this characteristic length scale where the stress saturates. I was very intrigued listening to Zhigang teaching fracture mechanics that this Revlin-Thomas pure shear model is giving us a sense of Griffith's type that says the toughness is about an energy argument. I really resent that so strongly. So I decided to ask students to experiment. And because I believe that this is all just about stress. So here's the stress you find. No matter what is your height, the fracture occurs at the same tip stress level. And you can look at this for different H's. You can look at that for, and you can collapse into a master curve when you use this loading parameter K to be related to height. Nothing new there. And in any case, we find that there is a different origin of why Revlin-Thomas works here. That works because the tip stress is reaching the same level, and the tip stress is enhancing more and more as you use higher height of your sample. So here's my trouble with fracture mechanics. Being a student at 60 years old, learning fracture mechanics. Imagine how much trouble that is. I had these two questions that I scratched my head. Gee, why this GC nevertheless is a constant? And what determines magnitude? Well, this operation, definition, this Griffith's result doesn't answer that question specifically. In particular, we know stress diverges, so there's this Irving way of remediate, right? And then what our experiment told you. Well, summarize what I told you in experiment. We find the stress behave this way instead. Tip stress linearly increasing as you load, instead of reaching a level right away. So with that, the rest is clear. It goes all the way to the tip, and we have a sense of what determines magnitude. That's why Griffith's scaling, the prefactor, which is Kc, is determined by. It's determined by the stress, tip stress at that point. And then there is a magic length scale that comes in, which essentially in linear elastic limit is the fracto-cohesive length. So learning all this, I realized all I learned about fracture mechanics can be captured in the older model 1913 of English. By the way, this scenario by Irving directly contradicts Iron's English result. English told us the tip stress should just linearly increasing with load. And this does not have that scenario at all. Moreover, push this way all the way to the point of fracture. K, of course, become Kc, this magic operational definition. But on the left, it tells me what is the material definition of Kc, because that's when the left reaching the strength. Therefore, I asked my own question. That's the strength. That is what determines why it's a constant and what determines the magnitude. So in summary, there's the operational way I learned about toughness, and there is the material way of what toughness is. In other words, there are two pairs of stress and length scale, both prescribes toughness, except I prefer to understand where it comes from. I know how you measure it, that's operational, but I prefer to understand where it comes from. It's coming from the structure of the material, the strength of the material. It's involving these two independent parameters. Details, I I kind of regret that I sent this paper to you guys, but some of you probably didn't read it before coming. I'm kind of joking, right? You expect me to go through this, 30 pages long. But I will in 10 minutes. So this result Michael showed, it's like the experiment did for me. Toughness goes as a square of the strength. Strength is proportional to the bond strength, nominal strength. So let me go through the rest of my talk. How am I doing? Okay, halfway through. Great. So why we look at this elastic fracture problem? It obviously intrigued Oscar. It intrigued Rome, and it certainly intrigued me because, irritably speaking, it is not a constant. Well, when you change rate, when you change the temperature. And now how do we understand it, right? That's the question. So let me go through this. This is uncut sample. I think the connection between cut and uncut will be clear soon. So this is uncut in 1960. We find that if you have a unnotched sample, you stretch, the slower you stretch, the lower the strength, nominal strength. So these are just 3 different rates. And then you do temperature dependence. This is a low temperature curve, and this is a high temperature curve plotted as function of rate. That's why I said I can do it in 20 minutes, because Ronald's covered all of it already. Look, you shift. Wonderful, wonderful. That was the moment when WF was first discovered, Michael. It must be a wonderful story. So it's viscoelasticity, as Ron said. Here is the viscoelasticity. But fine, this kind of shift works for rheology. I wrote a whole book on rheology. I understand it, fine. But when you have cross-linking, why the rate comes in this manner? That puzzles Oscar, actually. Why it's so pathetic when I stretch slowly, I only stretch this much. But if I do it fast, I can do this much. The literature explanation is, as Ron suggested, or revealed actually, it's viscoelasticity. I think Constantine also knows this very well. And that's the uncut. What about cut? Ron already reviewed it. Again, I'm reminding you it's viscoelasticity. These are the data, and this is Constantino's data. And Oscar so beautifully showed, whoa, it's not always rate dependent. This is rate dependent, but this is not. The rest is where all the interesting thing happens. So the big mystery Oscar raised to us is why on Earth this thing is a function. When I change rate, when I change temperature. Damn, this is really a problem. And the literature is reviewed by Rome already. It's trying to explain this thing. And Alan Gent, one floor below, before, we are one floor apart in our building. He came one day to me, he said, Shiqing, I got this one Armstrong. They drive me nuts. I don't understand it. That's 20 years ago. Well, don't ask me then. Why? It's because your strength is time dependent. I think it's back to Alan's talk earlier. All the complication is in the fact your strength is time dependent. Delayed fracture. This is the delayed fracture that shows how time secretly comes into the story. Stretch a piece of uncut sample, hold it at room temperature, 10-minute breaks, hold it at minus 10 degrees, it takes you a week before it breaks. Okay, that's that data. If you look carefully, it doesn't obey WF at all, by the way, quantitatively. Qualitatively, it might be. I just replotted data, so it looks more dramatically different. This is our own data showing the same thing. Okay, so what's going on? The polymer physics story now. I mean, My role is to show I learned a little bit of polymer physics, I learned a little bit of fraction mechanics. There are two time scales in the problem. There's the familiar polymer relaxation time, and there is the bond lifetime. This is without question. It's a question, I'll show you later that why we don't care about that previous. In any case, you can do density functional calculation and show exactly as I loaded the bond with more and more tension, the lifetime of the bond crashes down, okay? Crashes down. And at different temperatures, at a given level of tension, the bond lifetime is longer and longer if it's colder and colder. So you can go through the whole 9 yards about how to relate this bond tension lower the barrier. I'm just going to skip it because it's so boring. But it's known for since 1940s. The density functional calculation, of course, was more recent. It's 2000. So in any case, you can go through. Let me go through this whole thing for you one more time. There is the polymer relaxation dynamic. Okay, this is how the chains. I'm just picking up the chain, and you find out how do you find the relationship, meaning with respect to temperature. Well, this is one temperature, this is another, and then they shift. Why they can shift? Because that function, which is the so-called storage modulus, indeed is only a function of the product of the frequency times the relaxation time. Therefore, it works. So you can do detail and find indeed WRF type thing. So let me go to the dear question that we all had, the temperature and rate effect. So let me go through it very slowly. What does it do when you lower temperature? Three things happen. The bond lifetime is longer because there's no less energy available to hop over the barrier. Second, relaxation is slower. If you fix at the same rate, you end up effectively being able to stretch much more efficiently. Third, if you go toward glass transition, indeed you pick up a viscous stress. But I will show you that's nowhere near where we need to be to have the story understood. Rate effect, this is a marvelous thing. I think Oscar just said there are very little of that data. Indeed, we just published this data last year. So this is a sample that has a notch and different rate, different temperatures. They all fall on top of each other, indicating this is purely elastic stretching. But you can get so-called rate effect or viscoelastic effect. What really does this mean? This is Zhigang, you popularized that 3M sample. We use it day and night nowadays. So what happens? If you do birefringence, you show, the reason the stress is higher at higher rate is because I can pick up entanglement contribution now. Michael will love it. Okay, and you show the birefringence is higher because you pick up a different network structure. But to your disappointment, when you go to 90 degrees of the 3M sample, the curve collapses because the temperature is so high, your external rate never can be high enough in this range to pick up entanglement contribution. So this is an entanglement-free region in the sense. It collapses. Why? I can even show you, you do stress relaxation, stress doesn't relax. Purely elastic. The problem is much simpler. Okay, so I'm almost reaching the punchline. So, in the literature, we thought this was a viscoelastic problem, but it's not clear how does this come in to explain our pure elastic deformation problem here, okay? It's purely elastic deformation. On the other hand, of course, we know that transition can happen, except in the polymer literature, we don't think it's a dominant story. And I won't bore you with all the literature that says everything. I cited Constantino's paper saying, of course, we acknowledge there are such thing as breaking, but really, what does it do to us? So I'm come to the modeling part. I will spend 2 minutes on it, and then I want to show you the experiment that not only connect the previous two talk, but even connect to the earlier talk by Alan. So the chains are stretched. Even when it's fully stretched, it's only 4 piconewtons. There's a tiny bit of further stretching that reach the tension amount that lower the bond lifetime sufficiently to match with experimental timescale. I will not skip the details of the motivation. All the complication secret and the rich physics is in how to relate the subpopulation of bonds. When they break, you have fracture. For that subpopulation of strands, what would be the tension related to the nominal strands? That's the whole physics. I made an intelligent guess about what that curve is. It's hypothesis. It's not derived from hopefully simulation that we're trying to do will eventually illustrate that. And moreover, I focus on chain tension only in about 4 nanonewton region, because that is the region according to density functional theory, where the bond lifetime is in the relevant range, 1 millisecond versus a day or 2. So basically, you can depend on how you stretch, you have stretching time. And my theory is that the stretching time is waiting for the bond to break. And you plot those two dependence with respect to tension amount. Numerically, I can find, graphically, I can find a point. That's the crossing point in green there. And then that's the point where I can find out the rest. So this is the prediction. So we find just like what experiment shows. For example, how much I can stretch as a function of rate. I can stretch more as I use higher rate. But if I go to lower temperature, I can stretch more, even more. Therefore, the black is on the top of the red. So all this 9 yard is in there. Different rate temperatures, same thing. It's all in there. And one can even blindly shift this data again to get a master curve. The master curve occurs if these experiments involve the same bond level, bond tension level. Then according to the justification for that shift is because they share the same lifetime dependence on temperature. Then you can indeed have a master curve, except the physics is entirely, has zero to do with polymer dynamics, but everything to do with the kinetics of bond dissociation. Okay. So last is the most interesting part, actually. So some recent experiments. So this is motivating us to look at elastomeric fracture in an entirely different way. I'm the living molecules. I want to see how long I can last. And it turns out, using the 3M sample, we are reporting that there are 3 steps I did. There is a step strand, you hold it, and then see if it crack grows. Well, imperceptibly, it's growing very slowly. That's this line. But then at some moment, let me fast forward the movie. So I know it's just, I'm being pressed now. Didn't I have 5 more minutes? I said it. I'm solving all the problems here. After all, it's just coffee break, right? I can offer that to you. Right? I can offer that right to you. So actually, there is a UV transition when holding. The system is cooking up to have a different structure so that at the same G, it makes a transition between slow and fast. I know I don't have time. I'm just teasing you. And so this probably is more impressive and an interesting one. So you do the same, you stretch continuously. Oh, come on, I don't have patience. Come on, go. I really don't want to delay your coffee. So, but I shouldn't go more. So it's slowly doing it. Okay, that's the curve. It's doing it very slowly. And at one point it would jump. Oh, come on. I just didn't want to pass it at that point. So in any case, you go. And it's just a fabulous thing. And the third one, you can learn it. I'm not going to show it. You can preload it and introduce a notch. and then it makes the on its own. So that's it. So this, in fact, this all motivated by the theoretical picture. So there are more population joining for you to change from U to V type of propagation. It involves not finding a path. So didn't some people mention? So what Ron mentioned, it was rough when you have this erosive type of fracture, but it becomes very smooth when you have the fast propagation. So with that, I conclude basically, I think energy approach, it doesn't give me the insight that I could develop by looking at strength and stress, because it's time dependent. And I can show you why there is not a flow problem, because when the defects are as small as P, there is no defects. And I think we can explain everything, including Jiangshu's experiment. I think one of the comment here is, please, he did it properly. He did it actually exactly right. Please always report SS curve. Don't omit it, right? So that we know the strength was improving while you have a higher strength. Toughness. Sorry, thank you.
Yes, question from the audience.
A great talk, Shijing. So I may ask this on behalf of Shengqiang and Frank, probably, because I've seen that. So I remember in their paper, that strength or the local tip, that is not rate dependent, right? So
I skipped so much. So remember yesterday, Zhiqiang's collaborator had a talk about vitrimers, and right there, and oops, why didn't I go forward? That whole thing, my message was actually to show that this covalent bond system does the same thing. It makes UV transition. It's a discontinuous transition. It's first order. So physicists loves it. It has hysteresis, as I showed. I skipped all of it. This is interesting details. So this is a different rate, a different amount of step strand. Yeah. So we have a paper just submitted to talk about this. So I can talk all the details. Right. Michael. So it's all about bond breaking. Even in your very fast system, the tension is so high, the bond lifetime crashes to 1 picosecond.
Well, yes, but. So your first point was that there are advantages to stress view over an energy view. Yet Irwin's main contribution, I think, was to show an equivalence, and in particular, to show that there are universal features to the crack tip where energy and stress become interchangeable. So what do you have to say to that?
Michael, he was prepared, so because I have to talk to him. Oh, it's a beautiful question. I remember arguing with, trying to convince the younger generation my view about there's a causality between K versus G. I could say they're equivalent. The least I can say, I retrieve all the way back. I'm showing you today the advantage of looking the stress right here. Without that approach, I wouldn't have migrated into understanding the essence of elastomeric fracture, which is bond scission, which is a stress problem, which is a strength problem, which is a time-dependent problem, because the strength is time-dependent. And energy, I think I will be lost. I think nobody can dispute about that.
We'll dispute with you during the computer call.
Exactly. It's all private, the parts.
Okay, so then it's our coffee break.
Thank you.
Either you want to set up a poster, you have Polymer,